The long-run behavior tells us what's happening at the end of our graphs, but what we're interested in here, like with the intercepts, so x-intercepts, y-intercepts, things like that, is what's happening in the middle of our graph. So the long-run behavior will tell us how our graph begins and ends. So like, say we're going off to positive infinity on both ends. Connecting what's in the middle could look like anything. Like, well, okay, it can't look like anything, but the idea with a polynomial is that it'll be a smooth curve. And with that, it can be kind of like a roller coaster of going up and down and up and down and up and down. We need to know the behavior of, okay, how many times can we possibly turn going up and down? Also, like how many times do we intersect with the x-axis? And then we can also see where we intersect with the y-axis with that one y-intercept. So what we're going to do in this video here is talk about what's happening in the short run behavior. So we're looking at intercepts, but this is really tying to short run behavior. So with long run behavior, we were interested pretty much only in that leading term. With short run behavior, we're very much more interested in the entire polynomial. But the degree of our polynomial coming from that leading term can tell us a lot about our polynomial function and kind of give us an idea of what to expect. So a polynomial of degree n, that will have at most n horizontal intercepts. Meaning, whatever the degree is, that's how many times at maximum, at most, we can cross the x-axis. So if I have a degree 5 polynomial, at most I'll cross that x-axis 5 times. We may cross it 4 times, we may cross it 1 time. That's all okay. But if we're crossing 6 times, that shouldn't be happening. And then what we're going to do here is describe the turning point, so kind of these local minimum and maximum values. So if our polynomial is degree n, we will have at most n minus 1 turning points. So if we had a degree 5 polynomial, we could see at most 4 turning points, so we always bump that down by 1. We could have less, that's totally fine, but basically if I had a degree 5 polynomial, I couldn't see 5 turning points or more turning points. Okay, multiplicity of zeros. What we're going to do here is talk about if we have our polynomial in factored form. So factored form, we looked at that with quadratics. With polynomials, we can do this, but to a much larger extent of having just a bunch of different pieces multiplying with each other. And what could happen is if this is making, let's call this a polynomial p of x, and we have something multiplying with something else, multiplying with something else, multiplying with something else. We can have these binomials grouped in these parentheses, and altogether, if you FOILed it all out, you'd get this big, long polynomial. Then what could even happen too is on these parentheses, we could see exponents coming through, meaning maybe we'd see an exponent of 2, maybe we'd see an exponent of 3, and some of them might just have an exponent of 1. And really, like, we could go beyond that. We're really just going to focus on 1, 2, and 3. But what this is doing, this wording of multiplicity of zeros, is that when we have this factored form, it makes it really easy to graph those horizontal intercepts. So that's what this multiplicity of zeros means. Zeros is another word for horizontal intercepts, or x-intercepts. So the multiplicity means the exponent. So really, it's that when we have this factored form, we're evaluating the exponent on those sets of parentheses. So let's talk about what happens when we have a multiplicity of 1, a multiplicity of 2, and a multiplicity of 3. And Yes, let's just go with that for now. So this is talking about sorry, I'm gonna put some numbers in up here. Let's say we have x plus 1 times an x minus 2 squared times an x minus 3 times an x plus 4 cubed. Okay, that right there is a polynomial. And then each of these factors have a multiplicity. So like the x plus 1 has a multiplicity of 1 because that exponent is 1. X minus 2 has an exponent of 2 on it, so an x minus 2 squared. So that would be a multiplicity of 2. X minus 3 would have a multiplicity of 1 because there's just an exponent of 1 on that set of parentheses. And then x plus 4 cubed, that would have a multiplicity of 3 because of that exponent of 3. Now, each of these numbers gives us a 0 for our graph. It gives us a spot where we're crossing that x-axis. And this is tying to what we talked about with quadratic functions, where it's the opposite, like the sign changes, because it's like we're putting in 0 on the left-hand side of the equation here. So what we would have is like 0 equals x plus 1, which when we solve that would be x equals -1. We would also have an x minus 2 equals 0, which would solve and give us x equals 2. X minus 3 equals 0 would give us x equals 3. X plus 4 equals 0 would give us x equals -4. So we end up, in this case, with these 4 different horizontal intercepts. But then each of these have a multiplicity on them, as we were talking about. Like that x minus 1, so I know I already talked through these, but x equals -1 would have a multiplicity of 1. X equals +2 would have a multiplicity of 2 coming from that exponent. X equals 3 would have a multiplicity of 1 coming from that exponent of 1. And x equals -4 would have a multiplicity of 3 because of that exponent of 3 on that x plus 4. So we have our zeros, are those numbers for x, and we have these multiplicities. And what this multiplicity is going to do is tell us what our graph looks like as we hit that horizontal intercept. If we have a multiplicity of 1, what our graph is going to look like is that it graphs straight through. In fact, it almost looks linear if you zoomed in on the point. So what this could look like, say I have my graph, and I'm going to show 2 scenarios here. And let's say I show we're crossing the x-axis at this coordinate. What we would be doing is either we'd be coming from up above and going straight through below. So it would almost look linear. Or if we're below the x-axis, then what we would be doing is coming from below and going straight through to up above. So that's the behavior at that x-intercept. If we have a multiplicity of 2, or really an even multiplicity, it creates a bounce at those locations. So let's say there's 2 possibilities. So let's say I have my horizontal intercept. If I'm up above the x-axis, what happens is we come down, we hit that horizontal intercept, and then we go back up. So at that point, it looks like a parabola because of that multiplicity of 2, like our even powers. It all ties together. And then the other scenario is just if we were below the x-axis. So when we approach that x-intercept, we would connect and then bounce and stay below the x-axis. And then the multiplicity of 3 is where we flatten, much like what we see when we look at x cubed. So our 2 scenarios here would be, say I have my horizontal intercept. If we're starting above the x-axis, like we're coming down, and then we flatten across that x-intercept and then go through below. And if we started below, we would be coming up, flatten, and go up, like our cubic function. So the 0 itself, so like that x equals -1, 2, 3, and -4, that would tell us where to plot our point on the x-axis. But then that multiplicity, that exponent, tells us how the graph behaves at that point. So are we going straight through, bouncing, or flattening across? All right, so let's try this out with a few graphs here. So we're gonna find the vertical and horizontal intercepts, and really I'm gonna go ahead with the idea of sketching these polynomial functions, and then we'll get some more practice in the next videos too. So we have our first function is this t minus 2 squared. Sorry, I take it back. We're only gonna do our vertical and horizontal intercepts here. I'm just gonna get rid of these graphs. So let me just delete out these graphs. All right. Okay, we're just gonna focus on doing math here. So vertical and horizontal intercepts. So let's start with vertical intercepts, because those will be pretty straightforward, because that's just where we plug in 0. So for the vertical intercept here, I would just look at g of 0. So we'd have 0 minus 2 squared times 2 times 0 plus 3. So 0 minus 2 is a -2, square that for a +4. And then 2 times 0 is 0, plus 3 is 3. So that's 12. So we have this coordinate 0, 12. So there's our vertical intercept. Then the horizontal intercepts are just going to take a little bit more work. Not too bad when it's factored, but when we have to do the factoring, there could be a lot of steps. So the horizontal intercept is when our function equals 0. So what I'm doing here is solving 0 equals t minus 2 squared times 2t plus 3. Now, with this one, what we're going to have is we have things that are multiplying together that equal 0. So based on our product of zeros rule, it's that when we have pieces multiplying to equal 0, each piece needs to equal 0, or at least one of the pieces needs to equal 0. So we could have t minus 2 equals 0. With that exponent of 2, we just list that once. So we're just going to have t minus 2 equals 0. And then we're going to have 2t plus 3 equals 0. And then we're going to solve these. So I have a t equals +2, and then 2t equals -3, t equals -3 over 2. And something I just want to bring up here is the multiplicity. So that horizontal intercept of t equals +2, that has a multiplicity of 2. And this t equals -3 halves, that didn't have an exponent on that 0, so that has a multiplicity of 1. And what that tells me is that when I start plotting these points, if I was graphing this coordinate 2, 0, when I graphed it, there would be a bounce there. It would kind of like look like a parabola just at that point. And then that t equals -3 halves, with that multiplicity of 1, it would just pass straight through, almost like a linear function. So we get an idea of the behavior at those coordinates as well, based on that multiplicity. All right, so let's do the same thing here, but with a function that's not factored. So we have this f of x equals x to the 6th minus 3x to the 4th plus 2x squared. So let's start with the vertical intercept, because we don't need to do too much with it in terms of finding the vertical intercepts. This is where we plug in x equals 0. So we'll have 0 to the 6th minus 3 times 0 to the 4th plus 2 times 0 squared. All of that's just going to give us a big old 0. So that gives us a coordinate 0, 0. Then the horizontal intercept, and there can be more than one of these, so let's say intercept. is where we plug in 0 for f of x. So we're going to have 0 equals x to the 6th minus 3x to the 4th plus 2x squared. And now we are going to solve. And to do that, we are going to factor. So first thing we're going to do is take out the greatest common factor, which is x squared. So that's going to leave us with x to the 4th minus 3x squared plus 2. Now, this one's a little different, but we actually factor it in the same way that we would if this was quadratic. So for some side work over here, if we had x squared minus 3x plus 2, and we were factoring, we would have x minus 1, x minus 2. So two values that multiply to positive 2 and add up to negative 3. What's a little different here is that we have this x to the 4th and this x squared, but this works out nicely for if instead of having x minus 1, x minus 2, it's like having x squared minus 1, x squared minus 2. So that when you multiply those first terms, you have x squared times x squared, which is x to the 4th. Negative 2x squared minus 1x squared is a negative 3x squared, and then negative 1 times negative 2 is a positive 2. So factoring this, it's going to be an x squared minus 1, x squared minus 2. And let's see, we can use difference of squares with that x squared minus 1. So let's see, 0 equals x squared. This will be an x minus 1, x plus 1, and then an x squared minus 2. So we end up with 4 factors here: x squared, x minus 1, x plus 1, and x squared minus 2. So we end up with x squared can equal 0, x minus 1 can equal 0, x plus 1 can equal 0, and x squared minus 2 can equal 0. All right, x squared equals 0, take the square root of both sides. We're just going to get an x equals 0 there. So this is our coordinate 0, 0. And actually, I'm going to make a note here. Notice that it was squared, so this has a multiplicity of 2. So that means when we approach that origin, and actually let's take a look at the graph of this when we're done with it to see how our function bounces at that point. Then we have x equals positive 1, so that gives us a coordinate 1, 0, and that has a multiplicity of 1, since there's just an exponent of 1 outside of those parentheses. X plus 1 equals 0 would give us x equals negative 1, so we're getting the coordinate negative 1, 0, and that would have a multiplicity of 1. And then x squared minus 2 equals 0, so we would add 2 to both sides, take the square root of both sides, and when we do that, we actually get a plus or minus, so we'd get a positive square root of 2, and we would get a negative square root of 2. So get 2 points there, root 2, 0, and negative root 2, 0, each having a multiplicity of 1. All right, let's take a look at this graph here and see how these come together. So I'm just going to put my paper over there, and let's graph our function x to the 6th minus 3x to the 4th plus 2x squared. All right. So something I want to point out here that we're going to talk about when we start sketching, let's look at that leading term. So that leading term is x to the 6th. So that's an even power polynomial, which in general looks kind of like a parabola, especially in terms of the long run behavior. So when we look at our graph here, it's kind of like if I am way zoomed out, it does kind of look like a parabola. We're off at positive infinity on either side, which is exactly what we expect with that x to the 6th as the leading term. So that long run behavior is coming through there. And then what we just found was this short run behavior. So we started with that vertical intercept, which was 0, 0. Then we also found the vertical we have our horizontal intercept. So we have that 0, 0 that had a multiplicity of 2. And what's happening there is that we're coming from up above the x-axis, we hit 0, 0, and we bounce off of it so that we're going back up and staying above that x-axis. And then we have negative 1, 0, and we just pass straight through that. Positive 1, 0, passing straight through that. So that's the multiplicity of 1 coming through. And then we have negative root 2 and positive root 2. So it's a case where we have 5 zeros for our graph. And then in terms of turning points, let's see, we have 1, 2, 3, 4 turning points for this graph. So that's visually how those horizontal intercepts come through, as well as the multiplicity describing the behavior of the graph at those points.